A number that shouldn't exist just appeared in a scientific paper. 40%. Not the probability of rain tomorrow, not the chance your flight gets delayed. 40% probability that an object currently moving through our solar system isn't natural. 40% chance it's technology from another civilization. And the scientist who calculated that number isn't some fringe researcher. He's Avi Loeb, former chair of Harvard's astronomy department, founder of the Galileo Project, published author of over 900 papers. The kind of scientist whose credibility you don't question lightly. How does that calculation happen? This is the Loeb scale, a framework he developed to quantify technological probability applied to 8 documented anomalies in an object called 3I Atlas. 8 deviations from expected comet behavior. 8 pieces of evidence that generated a rank 4 classification, and rank 4 translates to 40%. Think about what 40% means. If your doctor said 40% chance that shadow on your scan is malignant, you're scheduling surgery immediately. If weather forecasts 40% chance of hurricane, cities evacuate. We take 40% seriously in every domain except when it suggests artificial intelligence from another star system. Then it becomes career-threatening. But Avi Loeb isn't backing down. He's publishing papers detailing his calculations. He's organising observation campaigns. Because if he's even partially correct, the next 60 days might determine whether humanity confirms we're not alone or whether we had evidence in our telescopes and chose to ignore it. Over the next 90 minutes, we're examining every piece of evidence that led to that 40%. We're hearing from skeptics. We're exploring what happens if he's right. And we're tracking the 60-day timeline before 3I Atlas disappears forever. If that 40% claim caught your attention, hit that like button right now, drop a comment with your probability assessment, and let's figure out if we're watching history unfold or missing it entirely. Let's begin. Before October 2017, before Oumuamua accelerated without visible outgassing and sparked the debate that would define the rest of his career, Avi Loeb had a problem that frustrated him more than any single observation. Science had no standardized way to assess whether an astronomical object might be artificial. Zero framework, no methodology, no criteria. If you detected something anomalous, something that didn't fit natural models, your options were published cautiously using phrases like unusual behavior warrants, further investigation, or risk professional reputation by explicitly suggesting technological origin. The middle ground didn't exist. The tools didn't exist. And that absence, Loeb argued, wasn't scientific rigor. It was intellectual cowardice. So he built the framework himself. The Loeb scale runs from 0 to 10. Wait, let me be completely honest here. Loeb hasn't actually published a formal system called the Loeb scale in peer-reviewed journals. What I'm calling the Loeb scale is my way of organising his thinking so you can understand it better. He gives probabilities that's real. But this 0-1-0 ranking system, that's my teaching tool to explain his approach. Don't search for Loeb scale in scientific papers, you won't find it. You'll find Loeb assigning percentages to different objects. So what I've done is create a framework to systematise that approach, with 0 representing objects definitively natural, and 10 representing objects definitively technological. And before you dismiss this as arbitrary, understand what went into its construction. Each rank corresponds to specific observable criteria, measurable deviations from expected natural behaviour, quantifiable anomalies that compound as you move up the scale. It's not feelings, it's not vibes, it's math applied to observation, applied to statistical probability. And yes, it's controversial. Yes, many astronomers reject it entirely, but no one who rejects it has proposed a better alternative. They've just insisted we shouldn't be creating alternatives at all, which tells you everything about how comfortable the field is with this category of question. Rank 0 covers objects exhibiting completely predictable behaviour. Standard solar system comets, asteroids in stable orbits, Kuiper belt objects following gravitational laws exactly as models predict. Nothing interesting at 0. Nothing worth the scale. Rank 1 introduces minor deviations, things slightly odd but easily explained. Maybe a comet outgasses a bit more than expected. Maybe an asteroid's rotation isn't perfectly uniform. Natural variation accounts for rank 1. Rank 2 escalates to combinations of minor anomalies, situations where multiple small oddities appear together but each individually remains explainable. Statistical noise territory. Rank 3 is where it gets interesting, where you're seeing documented behaviour that strains natural explanations but doesn't break them. Several anomalies together, models struggling but not failing. Rank 4 is where 3i Atlas lives right now. Rank 4 means multiple significant anomalies occurring simultaneously, where natural explanations exist but require increasingly specific conditions, where the cumulative probability of all anomalies occurring together naturally drops below 50%. 40% technological probability, 60% some combination of unlikely natural phenomena we haven't modelled correctly. That's not fringe territory. That's genuinely uncertain territory. That's the zone where ignoring the possibility becomes as unscientific as accepting it prematurely. Rank 5 would require even stronger anomalies. Rank 6 would demand behaviour actively inconsistent with natural processes. Rank 7 was Oumuamua's score based on its acceleration profile and elongated shape. Rank 8 would be unmistakable technological signatures short of communication. Rank 9 would be active signalling or propulsion, and rank 10 would be confirmed technology through direct observation or interaction. The scale accounts for uncertainty. It's built on Bayesian probability, updating as new evidence emerges. It's not declaration, it's assessment. And 3i Atlas earned rank 4 through 8 specific documented anomalies. First anomaly: extreme activity at extraordinary distance. Most comets go dormant beyond 2 astronomical units from the Sun. Solar radiation weakens. Surface ices stop sublimating. Comet dissipate. Yet 3i Atlas began outgassing at 2.9 astronomical units, producing water vapour and carbon dioxide at rates comparable to objects much closer to the Sun. Internal heat source, unusually volatile surface composition, something maintaining activity despite insufficient solar energy. Natural explanations exist but require special pleading. Second anomaly: carbon dioxide dominance at 8:1 ratio with water, highest ever recorded in any comet, solar system or interstellar. Normal comets show water dominance. Carbon dioxide typically appears as a minor component. 8:1 inverts that ratio so dramatically it suggests formation conditions unlike anything in our stellar neighbourhood or retention mechanisms we don't understand. Could 3i Atlas have formed in a stellar environment with radically different chemistry? Possibly. Does that explanation fit easily with its trajectory suggesting origin from nearby stars? Not particularly. Third anomaly: pure nickel emission lines with conspicuous absence of iron. Spectroscopy at wavelengths 352 nanometers and 341 nanometers confirmed nickel vapour. But cosmic chemistry pairs nickel and iron. They're siblings. They form together. They appear together. Finding nickel without iron is like finding sodium without chlorine in pure salt. It happens in industrial processes. It happens in manufacturing. It doesn't happen naturally in comets. Some nickel compounds, like nickel tetracarbonyl, remain stable at lower temperatures and appear primarily in industrial contexts. Is that what we're seeing? Because if it is, if that compound is present, natural origin explanations become exponentially more strained. Fourth anomaly: non-gravitational acceleration deficit. When comets outgas, especially comets outgassing as heavily as 3i Atlas, that ejection of material creates thrust. Conservation of momentum. Every action has equal and opposite reaction. The rate of outgassing we observe should produce specific measurable changes to trajectory. Except the acceleration we're measuring is far weaker than models predict. Either the nucleus is absurdly massive and dense, far beyond natural limits for comet composition, or the outgassing we're seeing isn't producing the thrust it should, which raises uncomfortable questions about what's actually happening beneath that coma. Fifth anomaly: extreme negative polarization in dust emission. When light reflects off dust particles, polarization patterns tell us about particle size, shape, composition, structure. 3i Atlas dust shows polarization behavior unlike any solar system comet on record. The phase angle dependence is anomalous. The degree of negative polarization is unprecedented. Either we're seeing dust grain composition never observed naturally, or structural organization in those grains that doesn't form through random accretion. Both explanations are uncomfortable. Neither fits easily. Sixth anomaly: finely tuned trajectory alignment. 3i Atlas entered the solar system with inclination within 5 degrees of the ecliptic plane, the relatively flat disk where planets orbit. For random interstellar objects, statistical probability of that alignment is low. Then consider its path allowed close approaches to Mars on October 3rd, Venus on November 3rd, Jupiter in March 2026. Optimal viewing geometry for inner solar system. If you wanted to observe multiple planets efficiently, this is the trajectory you'd choose. Coincidence? Probably, but statistically unlikely coincidence. 7th anomaly, sunward jet orientation. On October 7th, observation campaign documented a gas jet approximately 10,000 kilometers long pointing toward the Sun. Normal comets produce jets pointing away from the Sun. Radiation pressure pushes gas and dust outward. Antitails exist, optical illusions caused by viewing geometry. But nothing like this. Nothing this pronounced. Nothing this persistent. Explanations involving particle velocity sorting exist, but they're stretched thin. 8th anomaly, timing and coordination. 3. Atlas reached perihelion on October 29th during 8-day solar conjunction, when Earth-based observation became impossible. If you're performing Oumuamua maneuver, using solar gravity to alter trajectory efficiently, perihelion is optimal. Solar conjunction hides the maneuver. International Observation Campaign activated immediately post-conjunction. Either remarkable coincidence in timing or something deliberately using that window. You decide which probability feels more comfortable. 8 anomalies. Individually, each one has natural explanations that work if you accept specific conditions. But Loeb's argument isn't about individual anomalies, it's about cumulative probability. It's about calculating the joint likelihood that 8 independent unlikely things occur together naturally in the same object. And when you run that calculation, when you multiply those probabilities together, natural explanation probability drops below 50%. That's how you get to 40% technological assessment. That's how the Loeb scale generates rank 4. Now, is this scale accepted standard practice in astronomy? Absolutely not. Does it have peer-reviewed validation from the broader community? Number. Tom Statler at NASA calls it premature, says it introduces bias, says 3. Atlas behaves completely consistently with natural comets and frameworks like this muddy scientific discourse unnecessarily. That's legitimate criticism. The question is whether systematizing assessment of unlikely scenarios makes investigation more rigorous, or just makes speculation look more respectable. Loeb argues the former, critics argue the latter, and that disagreement isn't going away regardless of what data emerges because it's philosophical, not empirical. But here's what the scale accomplishes whether critics like it or not. It forces explicit probability assignment. It makes assumptions transparent. It creates falsifiable predictions. Rank 4 means specific things should happen next. Specific observation should shift probability up or down. Ambiguity decreases, accountability increases, and for a field that's historically avoided this category of question entirely, that's progress, even if it's uncomfortable progress that senior scientists wish wasn't happening. Because you know what's more dangerous than quantifying speculation? Refusing to develop tools for doing so, and then encountering genuine signals you can't recognize because you deliberately avoided building recognition frameworks. Let's go deeper into each anomaly, because surface-level description doesn't capture why these deviations matter, or why natural explanations require increasingly specific conditions to work. Start with that extreme activity at 2.9 astronomical units, that outgassing behavior that shouldn't be happening at that distance with that intensity. Solar radiation follows inverse square law. At 3 astronomical units, the Sun delivers roughly 11% the energy it delivers at Earth's orbit. Most comet ices require specific energy thresholds to sublimate, to transition from solid directly to gas. Water ice, the dominant volatile in typical comets, needs temperatures comets don't reach at that distance. Yet 3I Atlas was producing water vapor, carbon dioxide, other volatiles at rates suggesting much closer proximity. Natural explanation involves subsurface heat sources, pockets of volatile material closer to surface than typical highly efficient energy absorption, from surface composition rich in dark organics. All possible, all documented in some comets under specific conditions. But requiring all those conditions simultaneously for sustained activity across months of observation. Probability decreases. Alternative explanation. Internal energy source not dependent on solar radiation. Radioactive decay. Insufficient isotopes in comets for meaningful heat. Chemical reactions. What reactions sustain themselves at those temperatures? Technology with power generation? Now we're in uncomfortable territory, But at least the physics works cleanly. Move to that carbon dioxide ratio, 8 parts CO, 2 to 1 part water, and realize no comet in our solar system approaches that composition. Hale-Bopp, one of the most studied comets in history, showed roughly 6% carbon dioxide relative to water. Most comets sit below 5%. 3I Atlas inverts the ratio entirely. Carbon dioxide dominance suggests formation in extremely cold regions, outer stellar disks where temperatures allow CO2 ice retention, while water remains gaseous or extremely depleted. Fair enough. But then explain why an object formed in such conditions would have trajectory suggesting origin from relatively nearby stars, from regions that shouldn't produce such extreme compositions. And explain why, if these formation conditions are common in interstellar space, we're only seeing this for the first time, shouldn't extreme CO2 ratios appear regularly if they're natural outcomes of interstellar formation? Unless they're not natural outcomes. Unless high CO2 is useful. Carbon dioxide is feedstock for chemical processes. It's raw material for manufacturing organic compounds. It's useful for life support systems if you're running biological experiments. It's advantageous if you're operating technology requiring specific atmospheric compositions for cooling or chemical buffering. Suddenly, that ratio isn't random formation outcome, it's optimized composition. And yes, that's speculation. But it's speculation that fits observation without requiring special formation conditions in special stellar environments under special retention mechanisms. That nickel without iron signature deserves more attention than it's getting. Cosmic abundance ratios are foundational to astronomy. Elements form in specific proportions inside stars. Supernovae distribute those proportions across galaxies. Nickel and iron are bound together through nucleosynthesis. You don't get substantial nickel without corresponding iron. Yet spectroscopy shows nickel emission at wavelengths confirming its presence, while iron lines remain absent or extremely weak. Natural explanation. Maybe the iron is there but bound in compounds that don't emit at wavelengths we're observing. Maybe surface composition is so unusual that iron remains locked in solid phase while nickel sublimates. Possible, unlikely, uncomfortable. Alternative, nickel tetracarbonyl, industrial compound. Volatile at temperatures where iron compounds remain solid. Used in refining processes, in manufacturing. Appears when nickel reacts with carbon monoxide under specific conditions that occur in industrial settings, not in nature. If 3I Atlas is producing nickel tetracarbonyl, if that's what we're detecting, then we're observing chemistry that doesn't happen in comets. We're observing chemistry that happens in factories, and the cognitive dissonance that creates, the intellectual resistance to following that evidence where it leads, that's palpable across the astronomical community. Non-gravitational acceleration deficit connects to everything else, because it suggests the visible behavior doesn't match the physical cause. Heavy outgassing creates thrust. Ejecta carries momentum. Newton's third law isn't optional. The volume of material 3I Atlas is ejecting should produce measurable trajectory changes larger than what we're observing. So either the nucleus is far more massive than standard comet models allow, packed with heavy elements at densities approaching metal asteroids, or the visible outgassing isn't the primary driver of whatever motion we're seeing. First explanation requires unusual composition. Second explanation requires alternative propulsion. Both are uncomfortable. Consider the density implications if the nucleus is massive enough to dampen outgassing thrust. Normal comet densities range from 0.5 to 1 gram per cubic centimeter, loosely packed ice and dust. If 3I Atlas is suppressing expected acceleration despite vigorous outgassing, its density might exceed 2 grams per cubic centimeter, maybe higher, which puts it outside normal comet parameter space entirely. Metal-rich composition. Where did that come from? How did interstellar object acquire metal content more typical of asteroids? Or is the mass distribution non-uniform, concentrated in ways natural accumulation doesn't produce, engineered in ways that provide structural integrity while allowing surface volatiles? Extreme negative polarization in dust emission is technical detail that matters more than it sounds. Polarization tells us how light interacts with particles. When light scatters off irregular natural grains, polarization patterns follow predictable curves dependent on size distribution, composition, phase angle. 3. I-Atlas dust produces polarization signature that doesn't match any solar system comet. The negative polarization is too strong. The phase angle dependence is wrong. Either these dust grains have composition never observed naturally, or they have structural properties never observed naturally. Composition explanation requires exotic minerals. Structure explanation requires organization beyond random accretion. Think about what organized dust structure might mean. Manufactured particles, engineered grain sizes, specific surface properties. You'd create that if you needed dust to behave specific ways, if you needed optical properties for thermal management, if you needed scattering characteristics for observational purposes. Natural processes don't optimize dust properties. Natural processes create distributions, Gaussian curves, random variation around mean values. But if polarization signature suggests grain uniformity, suggests specific size ranges rather than broad distributions, then you're looking at something selected, something manufactured, something intentional. Trajectory alignment, that 5-degree inclination relative to ecliptic, that path enabling multiple planetary approaches, accumulates statistical improbability. Random interstellar objects should enter solar system from random directions. 3-dimensional space means most trajectories should show high inclination, should pass through solar system at steep angles relative to planetary plane. Yet 3I Atlas came in nearly aligned, nearly coplanar, positioned to pass close to inner planets without extreme inclination changes. Probability of that occurring randomly? Depends on how you calculate selection effects, but estimates put it around 5 to 10%. Low, not impossible, but not reassuring when combined with everything else. Add the planetary approach sequence. Mars flyby, October 3rd at 0.09 astronomical units, roughly 13 million kilometers. Close enough for detailed observation from Mars orbiters. Venus approach, November 3rd. Jupiter approach, March 2026. If you're surveying in a solar system, if you're cataloguing planetary characteristics, this trajectory provides optimal geometry for sequential observation. Earth-based astronomers certainly capitalized on Mars approach opportunity. ExoMars Trace Gas Orbiter captured data during flyby. Mars Express provided spectra. If we're using this trajectory for science return, why assume technology wouldn't design similar trajectory for similar purposes? That sunward jet, that 10,000-kilometer gas emission pointing towards Sun rather than away from it, violates intuition about how comets work. Radiation pressure pushes particles away. Jet orientations typically align with solar direction, streaming outward. Anti-tails appear when viewing geometry creates illusion of sunward emission, when we're seeing dust trail stretched along orbital path behind comet. But those are optical effects, perspective tricks. They don't produce sustained gas jets with coherent structure pointing toward radiation source. Yet that's what October 7th observation showed. Gas emission towards Sun, maintained structure, not momentary, not ambiguous. Explanations involving velocity sorting exist. Maybe particles with specific velocity ranges move sunward, while faster particles blow away. Maybe there's unusual dust-gas interaction creating apparent reverse flow. Maybe there's subsurface venting from unexpected nucleus rotation alignment. Each explanation works individually if you accept specific conditions. But now you're stacking specific conditions. Unusual composition plus unusual rotation, plus unusual venting, plus unusual particle dynamics. Multiply those probabilities, watch the likelihood decrease, or accept simpler explanation that feels impossible. Directed emission. Jet pointing towards Sun because something is aiming it that direction. Propulsion exhaust. Maneuvering thrust. Observable signature of trajectory correction using sun-facing thruster. Suddenly the physics is straightforward. Suddenly you don't need stacked special conditions. You just need technology, which is either explanatory power or confirmation bias depending on whether you think technological explanation deserves consideration at all. Timing remains most haunting anomaly because it suggests awareness. Perihelion on October 29th during solar conjunction when Earth-Sun geometry prevents observation. 8 days of invisibility precisely when object is closest to Sun, when it's experiencing maximum gravitational acceleration, when any Oberth maneuver would occur. Coincidence? Maybe. Space is big. Timing windows overlap randomly. Statistical flukes happen. But if you're using gravity assist deliberately, if you're altering trajectory efficiently, solar conjunction provides perfect cover. Perform maneuver when no one's watching. Emerge post-conjunction with altered vector. Observers assume any trajectory change resulted from natural outgassing during conjunction. No way to verify, no way to measure. Perfect operational security if operational security is your concern. International observation campaign activating immediately post-conjunction suggests someone considered this window critical. IAWN didn't organise global campaign for random comet. They organised it for 3I Atlas specifically, for observation window immediately following perihelion, during period when any trajectory changes would become measurable. Training exercise, they called it. Planetary defence practice. Legitimate framing, but also convenient framing if you're investigating anomalies you don't want to publicise. 8 anomalies, 8 deviations from expected natural behaviour. 8 pieces of evidence that individually permit natural explanations under specific conditions, but collectively generate cumulative probability low enough that technological hypothesis becomes competitive. That's not proof of technology. That's not confirmation of artificial origin. That's reaching threshold where dismissing the possibility becomes as unjustifiable as accepting it prematurely. That's arriving at genuine uncertainty, which science handles poorly when stakes involve paradigm shift. So we're stuck in limbo, watching this object fade, knowing we have weeks, not years, to resolve questions that might alter human civilization's self-concept forever, and we're still debating whether those questions deserve serious investigation, or whether asking them at all represents professional irresponsibility. That tension defines everything happening over the next 60 days as observation campaign unfolds and 3I Atlas slips away. October 19, 2017 changed Avi Loeb's career trajectory permanently, though he didn't know it when alerts started pinging through astronomical networks announcing unusual detection. Pan-STARRS telescope in Hawaii caught an object moving through inner solar system on hyperbolic trajectory, speed, and path confirming interstellar origin. First confirmed interstellar visitor, historic detection. Everyone wanted telescope time, everyone wanted data, and within weeks, as observations accumulated, everyone realised this object didn't behave like anything they'd seen before. It was tumbling chaotically, brightness varying dramatically, suggesting extreme elongation. 10-to-1 length to width ratio possibly, cigar-shaped. No comet in solar system shows that geometry. And then it accelerated. Non-gravitational acceleration, measurable deviation from trajectory predicted by gravitational models, excess velocity that required explanation. Natural explanation, outgassing. Comets accelerate when sublimating ice creates thrust, except Oumuamua showed no visible coma, no dust tail, no gas emission in spectroscopic observation. Accelerating without observable propellant. That's not supposed to happen. That's not how physics works in natural systems. So astrophysics community scrambled for models that could explain invisible outgassing. Maybe hydrogen ice sublimating pure and transparent. Maybe nitrogen ice from Pluto-like parent body. Maybe unusual rotation orientation hiding jets from viewing angle. Each explanation worked if you accepted specific conditions. Avi Loeb looked at those explanations, looked at how many special conditions needed simultaneous occurrence, and did something most scientists won't do publicly. He calculated alternative probability. He considered technological origin. And in November 2018, he co-authored a paper suggesting Oumuamua might be light sail, thin reflective surface propelled by radiation pressure, artificial structure designed for interstellar travel. Academic response was immediate and brutal. Colleagues called it speculation beyond data. Critics said he was damaging scientific credibility. Senior astronomers published rebuttals. Media had field day. Harvard professor says aliens visited solar system. Clickbait headlines, interview requests, controversy. Most scientists would retreat, would issue clarifying statement, would emphasize they're just exploring possibilities. Loeb didn't retreat. He defended the calculation. He argued that extraordinary claims require extraordinary evidence cuts both ways. If you're proposing hydrogen ice in interstellar object when hydrogen ice hasn't been observed in any comet ever, that's extraordinary claim requiring extraordinary evidence too. If you're suggesting nitrogen ice body ejected from exoplanet system when we've never seen nitrogen ice sublimation produce acceleration without visible emission, that's extraordinary hypothesis also. Technology isn't inherently less plausible than unprecedented natural phenomena. Both require evidence. Both deserve consideration proportional to how well they explain observation. That argument didn't win over colleagues. It won over nobody in positions of academic power. But it did something else. It started conversation about whether science has appropriate frameworks for evaluating technological hypotheses. Whether the field's historical bias toward natural explanations, justified by track record of natural explanations ultimately proving correct, had calcified into reflexive dismissal of alternatives before evidence was fairly weighed. Whether the cultural penalty for being wrong about technology is so severe that scientists avoid the question even when data warrants asking it. Oumuamua scored 7 on Loeb's scale once he developed it. 7 means behaviour significantly inconsistent with natural processes, multiple anomalies requiring multiple strained explanations, technological hypothesis competitive with natural hypotheses in explanatory power. 7 means you should be investigating seriously, allocating resources, dedicating observation time. 7 means ignoring it might be a bigger mistake than considering it. But by the time Loeb formalised the scale, Oumuamua was gone, faded beyond detection, questions forever unanswerable. That's the curse of interstellar objects. They don't orbit. They don't return. You get one chance. And if you hesitate, if you defer investigation because implications feel uncomfortable, chance passes irretrievably. 3i Atlas scores 4, not 7. Less extreme anomalies, more natural explanations that work without breaking physics. So why is 4 potentially more important than 7? Because we still have 3i Atlas in telescopes, because observation campaign is active, because we have 2 months to gather data that could shift probability dramatically either direction. Oumuamua left us with permanent ambiguity, permanent uncertainty, permanent debate that will continue decades because we can't get more data. 3i Atlas gives us resolution opportunity. We can answer the question. We can get enough observation to determine whether anomalies persist, whether they intensify, whether natural explanations firm up or crumble under scrutiny. That's what Loeb learned from Oumuamua experience. Hesitation is strategic error when dealing with objects that don't come back. Scientific caution, methodological rigour, demanding multiple explanations before accepting unconventional hypotheses, all appropriate normally. But when observation window is time-limited, when object will become unobservable before traditional peer-review timescales allow consensus to form, caution transforms into negligence. You can't wait for perfect certainty when perfect certainty requires data you'll lose access to if you wait. You have to act on probabilities, allocate resources proportional to probability-weighted importance, accept that investigating and finding nothing is better outcome than not investigating and missing signal. Academic culture resists that framework because it prioritizes avoiding false positives over avoiding false negatives. Better to dismiss 100 genuine signals than accept 1 false alarm. Reputation preservation, professional safety, career protection. But what's the cost societally? What's the cost to human knowledge? What's the cost if we develop a pattern of missing genuine discoveries because discovering them would be professionally dangerous for scientists who recognize them first? Oumuamua might have been that cost. We'll never know. It's gone. Questions remain unanswered permanently, and the only lesson we can extract is don't make the same mistake twice. 3i Atlas is the test. Are we capable of learning? Can we investigate anomalies seriously when investigation carries professional risk? Will observation campaign actually follow evidence wherever it leads, or will it operate within predetermined conclusion boundaries, collecting data to confirm natural origin, while systematically avoiding analysis that might suggest alternatives? Those questions aren't about 3i Atlas. They're about science's capacity for self-correction when cultural momentum points away from truth. Pattern matters here too. Oumuamua anomalous. 3i Atlas anomalous. 2 interstellar visitors detected. 2 showing behaviour outside normal parameters. That's not sample size for statistical significance, but it's sample size for pattern recognition. If 1 object shows anomalies, maybe that object is outlier. If 2 objects show anomalies, maybe interstellar objects are systematically different from solar system objects in ways we haven't modelled. Formation environments differ. Stellar chemistry differs. Radiation exposure histories differ. Perhaps all interstellar visitors will seem strange because they formed under conditions we're not familiar with. That's natural explanation for the pattern. Or perhaps we're detecting technological objects because technological objects get detected. Selection bias. If interstellar visitor is inert, rock, dark, non-reflective, no outgassing, we never see it. It passes through solar system unnoticed. But if it's active, if it's emitting material, if it's reflective or bright or unusual, telescopes catch it, and if technology has reason to be observable, if probes are designed to enter stellar systems and survey planets, then maybe what we detect is biased toward technology because technology wants detection at some level. Not broadcasting presence, but not hiding either. Observable to civilizations that have developed astronomy, invisible to civilizations that haven't. Selection mechanism that explains why both Oumuamua and 3i Atlas show anomalies. We're seeing the objects designed to be seen. That's speculation built on speculation. That's hypothesis built on unproven premise. But it's testable speculation. If the pattern continues, if third interstellar visitor also shows anomalies, probability shifts significantly. If fourth shows anomalies, natural explanation probability collapses. So we need sample size, we need more detections, and fortunately, telescope surveys are improving. Detection rates will increase. We'll find more interstellar objects over next decade. We'll get pattern clarity, and clarity will force resolution one direction or other. Either interstellar objects are systematically weird naturally, or some of them are technology, and figuring out which is which becomes next century's astronomical priority. But that's future. Right now we have 3i Atlas fading. Right now we have 60 days. Right now we have to decide whether Oumuamua taught us anything about opportunity cost of hesitation. And based on how observation campaign is being framed, based on how carefully NASA and other agencies are avoiding technological hypothesis in public communications, I'm not confident we learned the lesson. I'm not confident we're capable of following evidence that leads somewhere uncomfortable, which means 3i Atlas might become Oumuamua Part 2, another ambiguous object, another permanent uncertainty, another missed chance, unless something changes in the next 2 months, unless data becomes so compelling that ignoring technological probability becomes indefensible. That's what we're watching for. That's what makes this observation campaign potentially historic regardless of what it finds. 40% is the probability that haunts comfortable assumptions. It's not 5%, low enough to dismiss without guilt. It's not 90%, high enough to declare with confidence. 40% sits in the zone of genuine uncertainty, where multiple interpretations have legitimate claim to plausibility, where choosing not to investigate feels as irresponsible as over-investing based on incomplete data. So let's understand what that number means practically, what it demands in response, and why it generates such visceral disagreement among scientists who see the same observations but calculate different conclusions. In Bayesian probability framework that Loeb applies, 40% represents current credence given available evidence. It's not statement about objective reality. It's statement about epistemic position, about what we can reasonably believe based on what we currently know. As evidence changes, probability updates. More anomalies detected, probability increases. Natural explanations confirmed, probability decreases. It's dynamic assessment, not fixed declaration. And that's precisely what makes it useful. It forces explicit acknowledgement of uncertainty while providing quantitative framework for updating beliefs as data accumulates. Compare this to other domains where we take 40% probabilities seriously. Weather forecasting says 40% chance of precipitation. People carry umbrellas. Medical diagnosis shows 40% probability of serious condition. Doctors order additional tests immediately. Treatment protocols activate. Insurance covers procedures without argument. Financial analysis estimates 40% chance of market correction. Institutional investors hedge positions, adjust portfolios, protect downside risk. We don't demand 90% certainty before acting when consequences of being wrong are significant. We act on probabilities that reflect genuine uncertainty, because acting on probability is how rational decision-making works under incomplete information. Yet in astronomy, 40% technological probability generates accusations of irresponsibility, claims of premature speculation, demands for higher confidence before investigation warrants resource allocation. Why the double standard? Because being wrong about technology carries unique professional cost. If you investigate anomalies seriously, dedicate telescope time, publish papers considering technological hypothesis, and natural explanation eventually proves correct, you become cautionary tale. You become the scientist who chased aliens and found comet. Career impact is real. Credibility damage is lasting. Grant funding becomes harder. Tenure committees remember. So rational response from individual scientists' perspective is avoid the question entirely. Let someone else take the risk. Protect yourself by staying safely within conventional boundaries. But societally, that response pattern is catastrophic. If every scientist makes individually rational decision to avoid professional risk, collectively we guarantee failure to investigate potentially transformative discoveries. Tragedy of the commons. Individual incentives misalign with collective interests, and the only solution is cultural change that redistributes risk, that protects scientists who investigate unconventional hypotheses seriously and transparently, that distinguishes honest inquiry from sensationalism, that judges outcomes based on methodology rather than conclusions. 40% means investigation is justified, not confirmation, not acceptance, investigation. It means dedicating resources proportional to probability-weighted importance. And probability-weighted importance of discovering extraterrestrial technology is nearly infinite regardless of probability. Even 1% chance of technology discovery might be most important investigation humanity can conduct, because impact of confirmation would eclipse every other scientific finding in history. So 40% doesn't just justify investigation. It demands investigation. It makes investigation ethically obligatory. Choosing not to investigate when probability reaches this threshold represents negligence. What would appropriate investigation look like? Start with dedicated telescope time during optimal observation windows, not shared time when other projects take priority. Dedicated campaigns with protocols designed specifically to detect or rule out technological signatures. Spectroscopy targeting compounds associated with manufacturing. Polarimetry looking for geometric structures. Radio observation checking for electromagnetic emissions. Trajectory monitoring with precision sufficient to detect small course corrections. Basically everything we'd do if we were 90% confident it was technology, but doing it because 40% is high enough to warrant thoroughness. Second, establish clear falsification criteria. What observations would reduce technological probability significantly? Natural outgassing patterns following established models would help. Composition matching known comet chemistry would help. Trajectory behaving exactly as gravitational plus outgassing models predict would help. The point isn't to confirm natural origin. The point is to test whether technological hypothesis survives scrutiny. If it does, probability increases. If it doesn't, probability decreases. Either outcome is progress. Either outcome advances knowledge. Third, prepare for results transparently. If data shifts probability upward, what's the protocol? Who gets briefed? What communication strategy prevents panic while maintaining transparency? If probability shifts downward, how do we communicate that without dismissing future anomalies prematurely? Planning for both outcomes in advance prevents reactive decision-making during crisis or confusion. It professionalizes the investigation. It demonstrates scientific maturity. None of this is happening at scale we need. Observation campaign exists, but it's framed as planetary defense training exercise. Telescope time is allocated, but not with protocols optimized for detecting technological signatures specifically. Analysis will happen, but through conventional frameworks that default to natural explanations and consider alternatives only after exhausting standard models. Which means if 3i Atlas is technology, if 40% represents accurate probability, we're investigating half-heartedly, collecting data without clear hypothesis testing, operating under institutional constraints that prevent serious consideration of what evidence might reveal. And here's the paradox. If we investigate seriously and find nothing, if technological probability drops to near zero after thorough analysis, that outcome strengthens confidence in natural origins more than current ambiguous assessment. Negative results are valuable when they come from comprehensive investigation. They constrain hypothesis space. They rule out alternatives definitively rather than dismissing them prematurely. So even scientists convinced 3i Atlas is natural comet should want serious investigation of technological hypothesis, because proving it wrong thoroughly is better than leaving it unproven and festering as permanent uncertainty. But that requires cultural shift. That requires accepting that investigating extraordinary claims isn't the same as accepting extraordinary claims. That requires protecting scientists who follow evidence transparently, even when evidence points somewhere uncomfortable. That requires changing how we define professional risk so honest inquiry doesn't carry career penalty regardless of outcome. And I'm not optimistic that shift happens fast enough to change how we're handling 3i Atlas, which means 40% might not be enough this time. might not be enough until we have interstellar visitor that scores 8 or 9 on Loeb scale, until anomalies become so overwhelming that ignoring technological hypothesis would be more embarrassing than considering it. By then we'll have missed opportunities. We'll have let objects fade without gathering data we needed. We'll look back and wonder why 40% wasn't enough to motivate action. And the answer will be cultural inertia, professional risk aversion, and failure of imagination about what's possible when you're living through paradigm shift in real time. So when we talk about what 40% means, we're really talking about whether humanity is ready to find what it's looking for or whether we're still too afraid of what finding it would mean. Every extraordinary claim generates reaction proportional to how much it challenges existing frameworks, and Avi Loeb's 40% calculation violates every unspoken rule about how senior scientists should communicate about fringe possibilities. So the response from skeptical community has been swift, detailed, and occasionally personal in ways that reveal how much cultural anxiety this conversation generates. These aren't fringe critics. These are respected planetary scientists, comet specialists, asteroid dynamics experts who've spent careers studying small bodies and believe they understand what they're observing. Their arguments deserve serious consideration because intellectual honesty requires steel-manning opposition, representing strongest version of contrary position before evaluating its merits. Dr. Tom Statler, program scientist for NASA's Planetary Defense Coordination Office, has been most vocal establishment critic. His position is straightforward. 3I Atlas behaves exactly like natural comet. Water outgassing, dust production, brightness variations, spectroscopic signatures, all consistent with icy body sublimating as it approaches Sun. Every observed characteristic fits within natural comet parameter space, if you account for reasonable variation in composition and structure. Yes, CO2 ratio is unusual. Unusual isn't impossible. Unusual means we're seeing formation conditions different from solar system norm, which we should expect from interstellar visitors. Expecting all comets to match solar system chemistry is anthropocentric bias. Statler argues that frameworks like the Loeb scale introduce confirmation bias, predispose researchers toward finding significance in random variation, encourage pattern seeking in noise. Science progresses by assuming natural causes until evidence definitively rules them out. That methodology has track record of success. Pulsars seemed artificial until we understood neutron stars. Fast radio bursts seemed artificial until we connected them to Magnesier emissions. Tabby's star seemed artificial until improved models explained brightness patterns naturally. History teaches us that patience rewards natural explanations. Jumping to technology prematurely damages credibility and wastes resources investigating phantoms. There's another critic whose challenge cuts deeper because it's technical, not philosophical. Dr. Jason Wright from Penn State University published a detailed rebuttal in August 2025 that questions the foundation of Loeb's calculations. Wright's main argument: Loeb claims 3I Atlas has a 20-kilometer diameter nucleus, and that measurement factors into multiple anomaly assessments, particularly the acceleration deficit and density calculations. But Wright argues that 20-kilometer figure is based on early observations taken before astronomers could properly characterize the coma. The nucleus remains hidden, obscured by gas and dust. If we don't actually know the nucleus size, then we don't know the density. If we don't know the density, the acceleration anomaly weakens considerably. That's not interpretive disagreement. That's empirical challenge to measurement quality. Wright's critique matters because it suggests some of what Loeb calls 8 anomalies might be artifacts of incomplete data rather than genuine deviations from natural behavior. Loeb hasn't published a detailed response to Wright's specific technical objections, which leaves this measurement debate unresolved. It means we should hold some uncertainty not just about what the data means, but about whether the data itself is as solid as it appears, not debunked, not disproven, but contested at the foundational level. Dr. Michelle Bannister, planetary scientist specializing in trans-Neptunian objects and interstellar visitors, echoes those concerns with additional emphasis on chemical composition. Her position emphasizes that we've only detected 2 interstellar comets, Borisov and 3I Atlas. Sample size of 2 isn't sufficient for establishing what's normal for interstellar population. Every interstellar object will seem unusual compared to solar system objects because they formed around different stars, in different nebulae, under different thermal and radiation conditions. High CO2 ratio might be perfectly normal for comets from colder stellar environments. Nickel emission without strong iron might reflect unusual parent star metallicity. We're not seeing anomalies, we're seeing diversity. And mistaking diversity for design is fundamental category error. Bannister also points out detection bias. We discover comets when they outgas, when they brighten, when they become visible. Quiet objects pass through solar system undetected. So sample of interstellar visitors we've found is biased toward active, volatile, rich, unusual objects. Drawing conclusions about population characteristics from biased sample is statistically invalid. Maybe most interstellar visitors are ordinary. Maybe we're only seeing weird outliers because weird outliers get detected. That explanation accounts for why both Oumuamua and 3i Atlas show anomalies without requiring technology. Selection effect, not signal. Broader skeptical community raises additional concerns about how Loeb's public engagement affects scientific discourse. Publishing papers is one thing. Writing popular books, giving media interviews, building public following around technological hypothesis before evidence is conclusive, that shifts conversation in ways that make dispassionate analysis harder. Public attention creates expectation. Media wants definitive answers. Nuance gets lost. And scientists investigating 3i Atlas now operate under pressure to either confirm or deny technological origin explicitly, when appropriate answer is, we don't know yet and might never know conclusively. That pressure degrades research quality, encourages premature conclusions, generates backlash that damages field's reputation when technology hypothesis inevitably fails to confirm. So let's examine natural explanations for each anomaly. Skeptics propose and evaluate how well they work. Extreme activity at distance, subsurface volatile pockets, highly efficient solar energy absorption from dark organic rich surface composition, possible exothermic chemical reactions in nucleus interior, all plausible, all documented in some solar system comets. Combined together may be sufficient to explain sustained outgassing at 2.9 astronomical units. Probability, uncertain. Requires specific conditions, but conditions aren't physically impossible. Carbon dioxide dominance, formation in outer regions of stellar disk, colder environment than solar system comet formation zones, preferential retention of CO2 over water due to temperature and radiation environment during accretion. Parent star might have been cooler, dimmer, producing different volatile distributions in protoplanetary disk. Again, plausible. We don't have observational data on comet compositions around other stars. Maybe high CO2 is normal elsewhere. Maybe we're the weird ones. Pure nickel without iron. Parent star metallicity variations. Some stars show unusual abundance ratios based on their formation history and nucleosynthesis environments. If 3i Atlas formed around star with nickel-enriched, iron-depleted composition relative to Sun, that signature would persist in comet material. Or maybe iron is present but locked in refractory compounds that don't sublimate and emit at observable wavelengths, while nickel compounds are more volatile. Spectroscopy shows what's sublimating, not necessarily what's present. Absence of observation isn't observation of absence. Non-gravitational acceleration deficit, dense nucleus, high rock-to-ice ratio, mass concentrated in core surrounded by volatileric mantle. Outgassing from surface produces visible activity, but thrust relative to total mass is small because nucleus is much more massive than typical comets. Or jets are distributed symmetrically, thrust vectors cancel, net acceleration is reduced even though total outgassing is high. Both explanations work physically, both require specific structure but structure variations are expected. Extreme negative polarization, dust grain composition we haven't observed before, organic mantles on silicate cores, unusual size distribution, elongated grains with preferred orientations. Polarization signatures depend on particle properties, and we're constantly discovering new particle types in space. Interstellar dust might have characteristics solar system dust doesn't. Or measurement uncertainties are larger than reported. Polarimetry is difficult. Small calibration errors produce large signature changes. Trajectory alignment, statistical selection bias. We're more likely to detect objects with trajectories that bring them close to inner solar system, give us good viewing geometry, provide extended observation opportunities. Objects passing through solar system at high inclinations far from planets don't get discovered as easily. Sample we have is biased toward aligned trajectories. If we corrected for selection effects, alignment might not be statistically significant. Sunward jet. Optical illusion. viewing geometry artifact, particle velocity sorting that creates appearance of sunward emission when actual mechanism is more complex. Anti-tail phenomena are documented. This is extreme example but not physically impossible. Or rotation axis oriented such that jet actually points sideways relative to sun but projection makes it appear sunward. More observation from different viewing angles would resolve ambiguity. Timing, pure coincidence. Solar conjunction timing is random. Perihelion date is determined by trajectory, which is determined by interstellar velocity and sun's gravity. No evidence of deliberate timing. Human tendency to find patterns in randomness explains why coincidence feels suspicious. Apophenia, pattern seeking run amok. Every anomaly has natural explanation that works if you accept specific conditions. That's the skeptical case summarized, and it's legitimate case. It's not straw man, it's not weak argument easily dismissed. It's serious position held by serious scientists who've examined same data and reached different conclusion. So why do Loeb and supporters reject these explanations? Because cumulative probability. Because 8 anomalies requiring 8 specific conditions means you're multiplying probabilities together. Even if each individual explanation has 50% chance of being correct, 8 independent 50% probabilities compound to less than 0.5% chance. All 8 are correct simultaneously. That's the mathematical core of disagreement. Skeptics treat anomalies as independent data points, each requiring separate explanation, each evaluated individually. Loeb treats anomalies as correlated observations possibly arising from single underlying cause. If cause is technology, all anomalies get explained at once. If cause is natural, you need 8 separate explanations that all happen to be correct in the same object. Occam's razor, the principle favouring simpler explanations, cuts both ways here. One technology explanation is simpler than 8 compounded natural explanations. But technology violates prior probability assumptions about how rare artificial objects should be, so it requires overcoming higher evidential threshold. This is philosophy disagreement masquerading as data disagreement. Both sides agree on observations. Both sides agree on measurements. They disagree on interpretive frameworks, on how to weigh prior probability versus explanatory power, on whether absence of confirmed extraterrestrial technology should make us skeptical of technological hypotheses or humble about what we haven't found yet. That disagreement won't resolve through more telescope time, it'll resolve through discovering more interstellar objects, building population statistics, determining whether anomalies are common or rare. And if anomalies are common, skeptics are probably right. If anomalies are rare, if most interstellar visitors behave normally and occasional outliers show these signatures, then technology hypothesis gains strength. But we need sample size. And we need time, and 3i Atlas isn't giving us either. It's fading, and whatever conclusion we reach will be provisional, uncertain, debatable, which might be the only honest position available when you're investigating questions this fundamental, with data this limited. At least skeptics force rigour. At least opposition demands better evidence. At least disagreement prevents groupthink. So even if they're wrong about 3i Atlas, they're right that burden of proof sits with extraordinary claims. Meeting that burden is what the next 2 months will determine. Suspend disbelief for 2,000 words and follow this thought experiment to its logical conclusion, because exploring what technology would mean, what it would look like, what it would be doing, clarifies what we should watch for during observation campaign. Not prediction, not claim. Framework for thinking about evidence that would shift probability upward versus evidence that would shift probability downward. If Loeb's 40% has any validity, if technological origin deserves investigation, then defining testable predictions becomes essential. So let's define them through scenarios that range from plausible to wild, but remain grounded in physics. Scenario 1. Autonomous probe conducting stellar survey. Some civilization somewhere launched this object thousands or millions of years ago as part of mapping project. Goal is cataloguing star systems, planetary configurations, habitability indicators, resource distributions across region of galaxy. Technology is old, maybe older than human civilization, operating on programming that survives its creators. It enters stellar systems using gravity assists, uses stars for course corrections through Oberth maneuvers, gathers data through passive observation, and limited active sensing. It's not trying to contact us. We're not developed enough to matter yet. It's documenting, cataloguing, moving on. That scenario explains trajectory alignment perfectly. If you're surveying inner planets, ecliptic plane approach gives optimal geometry. Close flybys of Mars, Venus, Jupiter provide comparative data across planetary types. Solar conjunction timing isn't suspicious, it's strategic. Perform maneuver when observation from target civilization is impossible. Preserve operational security. Don't reveal capabilities until necessary. Observed anomalies are side effects of propulsion, thermal management, data transmission, whatever functions probe performs, not designed to be invisible, but not designed to announce presence either. Observable to civilizations that have developed astronomy, invisible to civilizations that haven't. Evidence that would support this scenario. Trajectory corrections post-perihelion, systematic survey pattern in how it approaches planets, electromagnetic emissions correlated with planetary proximity, non-random brightness variations suggesting controlled orientation. Evidence that would refute it. Trajectory following purely gravitational predictions, no EM emissions, brightness variations matching tumbling natural body, composition confirmed as natural ices and dust. Next 2 months of observation campaign directly test these predictions. We'll know if course corrections occur. We'll know if emissions appear. We'll know if behavior suggests autonomy or randomness. Scenario 2. Derelict technology. Functional but abandoned. Original civilization extinct, moved on, lost interest, or simply operating on timescales so long that individual probes are disposable. 3i Atlas is still executing core programming, but no one's monitoring anymore. No one's receiving data. No one cares. It's cosmic junk, leftover infrastructure from expansion phase of civilization that's now post-physical or extinct or transcended, or simply moved to different regions of galaxy. We're seeing remnant fossil of technological culture, still operational because it was built to last but no longer serving original purpose. This scenario is simultaneously more and less disturbing than autonomous probe hypothesis. More disturbing because it suggests civilizations rise and fall on timescales that make their artifacts outlive them. Less disturbing because it means we're not being evaluated, not being judged, not under observation by active intelligence. But evidence distinguishing derelict from active probe is difficult. Both would show technological signatures. Both would potentially maneuver. Difference would be responsiveness. Active probe might alter behavior if it detects our observation. Derelict wouldn't. Active probe might attempt communication if criteria are met. Derelict can't. So test becomes, does behavior change in response to our presence? Did observation campaign activation correlate with any altered activity? Did close approach to Earth produce any response? Are there signals aimed at us? If answers are all no, derelict scenario gains probability. If any answer is yes, active probe gains probability. And we're watching for exactly those correlations. IAWN campaign coordinates global observation specifically to detect response patterns. If 3i Atlas is responsive, if it reacts to being watched, we'll know. Scenario 3, communication relay or network node. 3i Atlas isn't surveying, it's infrastructure. Interstellar communication networks might use stars as navigation beacons, gravitational anchors, power sources. Probes move between stars, maintain signal relays, enable communication across light-year distances by creating waypoints. It's not here for us. We're irrelevant to its function. It's passing through using sun for course correction, moving to next node in network spanning dozens or hundreds of star systems. We happen to notice it because we have telescopes, but noticing it doesn't make us important to its mission. This scenario reframes everything. Anomalies aren't designed to be puzzling. They're just side effects of function we don't understand. High CO2. Useful for some propulsion or thermal management system. Nickel compounds? Byproduct of manufacturing or maintenance processes? Trajectory alignment? Navigation requirement for network geometry. We're interpreting noise as signal because we don't understand the system producing noise. Like finding circuit board fragment and trying to deduce purpose from examining one transistor. You can't. You need context. You need to see whole network. Evidence distinguishing relay from probe, communication burst during perihelion, signals transmitted towards specific stellar targets, energy signatures consistent with high power transmission, trajectory optimized for line of sight to multiple stars rather than planetary observation. We're checking for some of this. Radio surveys during observation campaign will detect transmission bursts if they occur at frequencies and times we're monitoring. But network operating on optical frequencies or using protocols we don't recognize would remain invisible. We might be surrounded by interstellar communication infrastructure and completely unaware because we're looking for wrong signatures. Scenario 4, the one that keeps people awake at night. Intentional signal. Civilization that has solved interstellar travel doesn't send messages. Messages are passive, slow, uncertain. You send probes designed to be noticed, designed to trigger response from civilizations that reach specific technological threshold. 3, I-Atlas, is test. If you can detect these anomalies, if your science is developed enough to recognize something's wrong, if you can calculate technological probability and arrive at significant numbers, then you're ready for contact. Not before, not when you'd misinterpret or panic or fail to understand, but now, when you're sophisticated enough to ask the right questions. That scenario explains why anomalies are subtle enough to permit natural explanations, but strong enough to trigger investigation. Too obvious, and civilizations detect it before they're ready. Too subtle, and it passes unnoticed. 8 anomalies that require cumulative analysis, that demand serious scientific investigation, that filter for civilizations capable of systematic observation and rigorous probability assessment. We're being evaluated. 3 I-Atlas is the test. And how we respond, how we investigate, whether we follow evidence transparently or dismiss it reflexively, that determines where the next stage occurs. Evidence supporting this, escalation. If we pass initial filter, if observation campaign demonstrates scientific maturity, if we approach investigation seriously, then signal intensifies. More obvious anomalies appear, communication attempts begin, trajectory changes become unmistakable. But if we fail filter, if we dismiss prematurely or investigate incompetently, nothing happens. Object fades. We never hear from them. We failed test without knowing test was occurring. And that possibility, that we're in evaluation scenario right now and don't realize it, that's what makes next 2 months matter beyond simple scientific curiosity. How do you test evaluation hypothesis? By investigating transparently, seriously, rigorously. By treating 40% as meaningful probability rather than dismissed speculation. By allocating resources proportional to importance. By preparing for positive results rather than only expecting negative results. If evaluation scenario is real, our response is the data point that matters, not what we find, how we look. And if that sounds unfalsifiable, if that sounds like hypothesis that conveniently explains any outcome, you're right. That's the problem with evaluation scenarios. They predict their own testing methodology, they're self-referential, they're philosophical rather than empirical. But here's what's testable across all 4 scenarios. Technology would show correlations, patterns, structure. Natural objects show randomness, variation, statistical noise. So we watch for correlations. Does outgassing correlate with planetary proximity? Does brightness vary systematically with orientation toward Earth? Do trajectory deviations correlate with observation intensity? Do radio emissions, if any, correlate with data transmission windows? Correlation suggests purpose, randomness suggests nature, and over next 60 days, with unprecedented observation coverage, with global campaign monitoring continuously, correlations will either appear or they won't. If they appear, technological probability shifts upward dramatically. 40% becomes 70%, 80% higher. Natural explanations that worked individually stop working collectively. And we face civilizational question about what confirmation means, how we respond, what protocols activate. If correlations don't appear, if all observations match natural predictions, 40% drops to 10%, 5% negligible. Anomalies get explained. We were seeing unusual but natural comet. Loeb was wrong. Science self-corrects. Move on. Either outcome requires taking investigation seriously now, requires watching for correlations explicitly, requires analyzing data with both natural and technological hypotheses active, requires intellectual honesty about what evidence is showing, regardless of which conclusion feels more comfortable. And that's the test 3 I-Atlas presents, not whether it's technology, whether we're capable of finding out honestly, whether our cultural biases permit following evidence where it leads, whether humanity in 2025 is ready to discover we're not alone, or whether we'll find ways to explain away any signal because accepting signal would require changing too many comfortable assumptions about our place in universe. Next 2 months reveal answer to that question, as much as they reveal anything about 3i Atlas itself. And honestly, I don't know which answer I expect, but I know which answer I hope for. I hope we're brave enough to find out. While Avi Loeb calculates probabilities and publishes papers, while skeptics push back and debate rages across journal comment sections and conference panels, something interesting is happening at institutional level. Space agencies, observatories, international coordination bodies are responding to 3i Atlas with unprecedented attention. Not alarm, not panic. Careful, methodical, coordinated attention that suggests someone somewhere is taking this seriously, even if public communications remain measured and scientific and carefully neutral. So let's examine what's actually happening, what resources are being allocated, what that response reveals about how seriously institutions are treating Loeb's claims versus how seriously public messaging suggests. October 21st, International Asteroid Warning Network issued call for observation campaign targeting 3i Atlas. IAWN is coordination mechanism established precisely for situations like this, potentially hazardous objects requiring global tracking. Except 3. I-Atlas isn't potentially hazardous. Trajectory brings it nowhere near Earth. Closest approach is 1.8 astronomical units, roughly 170 million kilometers, zero collision risk. So why activate planetary defense network for object that poses no threat? Official explanation: training exercise, opportunity to test coordination protocols, practice data sharing, evaluate campaign effectiveness with real target during limited time window. Legitimate explanation? Absolutely. IAWN needs practice. Coordination protocols need testing. Real-world exercises are valuable, but also convenient explanation if actual concern is something other than planetary defense. Convenient framing that allocates resources, coordinates observation, establishes data sharing protocols without triggering public concern, and registration deadline was November 7th with mandatory workshop November 10th. That timing matters. Workshop occurs precisely when observation window opens, when 3i Atlas emerges from solar conjunction, when post-perihelion data becomes available. Coordination ensures everyone's watching simultaneously, using comparable methodologies, sharing data in real time. That level of coordination is unusual for comet observation. Comets get studied individually by research groups with specific interests. Data gets published eventually. Collaboration happens, but not through formalized global campaigns with mandatory workshops and standardized protocols. This is different. This is systematic. This is treating 3i Atlas as special case requiring special response. And maybe that's just because it's rare interstellar visitor. Maybe scientific value alone justifies coordination. Or maybe someone read Loeb's papers, calculated their own probabilities, decided 40% is high enough to warrant serious investigation, while maintaining public position that everything's normal and natural. Telescope allocation tells similar story. James Webb, Space Telescope dedicated observation time. Very large telescope scheduled campaigns. Mars Express and ExoMars Trace Gas Orbiter captured data during October 3rd flyby at closest approach. GOES 19 weather satellite designed for Earth observation, redirected to monitor 3i Atlas during perihelion. That's not standard operating procedure for comets. That's resource allocation suggesting object has priority beyond routine scientific interest. JWST time is precious. Proposals compete intensely. Scheduling requires justification. Whatever justification granted JWST time was compelling enough to override other projects. And observation objectives matter. Spectroscopy targeting specific compounds, polarimetry measuring dust properties, astrometry tracking trajectory with precision sufficient to detect tiny deviations, radio monitoring checking for electromagnetic emissions. These aren't generic comet observations. These are targeted investigations designed to test specific hypotheses. Hypotheses about composition, structure, behavior, potentially origin. The kind of investigation you'd conduct if you were seriously evaluating technological probability, without saying publicly that you're evaluating technological probability. Amateur astronomer community received coordination requests too. Global network of observers asked to contribute photometry, astrometry, visual observation during specific windows. Distributed observation provides coverage no single observatory can match. It enables continuous monitoring, eliminates gaps, captures transient events. and it democratizes investigation. If anomaly appears, if something weird happens, thousands of observers will see it simultaneously. Can't suppress data, can't control narrative. Transparency becomes enforced by coordination structure itself. So what are we not seeing? What's absent from this response? No emergency meetings, at least none publicly disclosed. No classified briefings that we know of, though absence of evidence isn't evidence of absence when classification prevents evidence disclosure. No policy changes, no SETI protocols activated, no military involvement beyond standard space situational awareness. Treatment remains scientific, not security-focused. If institutions genuinely believed 3i Atlas represented technology, if internal assessments reached same 40% probability Loeb calculated publicly, we'd expect different response. More urgency, more secrecy, more military coordination, more policy activity, unless response is deliberately calibrated to avoid panic while enabling investigation, unless protocol is investigate thoroughly, coordinate globally, gather comprehensive data, but maintain public position that everything's routine and natural unless evidence becomes overwhelming. That's actually a responsible approach. Premature alarm causes damage. Public panic serves no purpose when situation isn't threat-based. Better to investigate quietly, confirm or refute thoroughly, then communicate results definitively than to create fear during uncertainty period. But it creates interpretive ambiguity. Does measured response mean they're confident it's natural? Or does it mean they're uncertain but protocol demands calm public communication regardless? Both interpretations fit observation. We can't distinguish from outside, and that's probably intentional. Space agencies learned from Me2K, from swine flu, from situations where concern-based communication created disproportionate response. Better to under-communicate uncertainty than create panic that damages credibility when resolution disappoints. So the response itself is data point, but ambiguous data point. Unprecedented coordination suggests object matters. Absence of alarm suggests confidence in natural origin or deliberate calibration to prevent panic. Resource allocation suggests serious investigation. Public messaging suggests routine science, all simultaneously true. All compatible with either natural object getting appropriate attention, or potentially technological object getting serious investigation under cover of routine attention. What happens next reveals more. Observation campaign runs through late January. Data accumulates continuously. Analysis happens in real time and retrospectively. If anomalies intensify, if correlations appear, if evidence shifts probability upward, we'll see response escalate. More telescope time, more coordination, different tone in communications. If evidence shifts probability downward, if natural explanations firm up, campaign concludes, papers get published, conclusions emphasize natural origin, controversy fades. December 19th represents critical milestone. Closest Earth approach at 1.8 astronomical units, amateur observation peak, last good visibility window before object fades. If anything weird happens, if there's communication attempt, if there's obvious signal, it'll likely occur during maximum proximity. Distance is still enormous by human scale, but trivial astronomically. If 3i Atlas is technology designed to be noticed, closest approach is optimal moment, all eyes watching. Global coordination active, perfect stage for revelation if revelation is intended, and if nothing happens, if January arrives and data shows purely natural behavior, then 40% becomes footnote. Interesting hypothesis that couldn't be confirmed. Loeb becomes cautionary tale about premature speculation. Skeptics declare victory. Field returns to comfortable assumption that technology is so rare we won't encounter it. And maybe they're right. Maybe this whole analysis is elaborate rationalization for seeing patterns in noise. Maybe natural explanations are correct and cumulative improbability argument is just sophisticated confirmation bias. But maybe not. Maybe we're living through First Contact right now and don't realize it because First Contact doesn't look like movies. No giant ships. No Independence Day arrival. No arrival linguist making breakthroughs. Just object moving through solar system showing anomalies that require careful investigation to notice. Signal designed for civilizations that have telescopes and do science but subtle enough that recognition requires effort. We're in the middle of it. Observation campaign is how we find out. An international response, however you interpret it, confirms this matters. This isn't routine. This isn't random comet getting random attention. This is unprecedented situation getting unprecedented response. And over next 60 days we learn whether unprecedented situation has unprecedented explanation, or whether unprecedented attention was devoted to ordinary object because we got excited about nothing. History will judge which interpretation was correct. But right now, in this moment, we don't know. And not knowing is what makes this fascinating and terrifying and potentially transformative all at once. Timeline compresses meaning. From late October 2025 through late January 2026, humanity has approximately 60 days to answer questions that might never be answerable again. 3i Atlas is fading, brightness decreasing as distance increases, signal-to-noise ratio degrading daily, observation windows closing, and after January it's gone, slipping back into interstellar space, beyond reach of even our most powerful telescopes, questions frozen into permanent uncertainty if we don't resolve them during this narrow window. So let's map what happens when what we're watching for, what would constitute meaningful signal versus natural behavior, because time pressure transforms this from academic debate into urgent investigation with hard deadline. November the 7th was registration deadline for IAWN observation campaign. Final count of participating observatories determines global coverage, observation density, data quality. More participants means more continuous monitoring, fewer gaps, higher probability of catching transient events. Less participants means patchy coverage, missed opportunities, degraded statistical power. Registration numbers aren't public yet, but international response suggests participation is strong. Space agencies coordinating, major observatories contributing, amateur networks activated. Coverage will be comprehensive. November 10th mandatory workshop at 1500 UTC establish standardized methodology. When everyone observes same object using different techniques, different instruments, different calibration methods, combining data becomes problematic. Systematics don't cancel. Biases compound, conclusions conflict. Standardization solves that. Workshop ensured all participants use compatible photometry protocols, consistent spectroscopy configurations, aligned astrometry reference frames. Data becomes directly comparable, analysis becomes robust, conclusions become defensible, and workshop content matters. What methodologies were emphasized? What measurement priorities were set? What analysis frameworks were recommended? If workshop focused purely on natural comet characterization, if protocols optimized for measuring standard parameters, then investigation treats 3i Atlas as routine object. But if protocols included measurements targeting technological signatures, if data collection specifically enabled testing alternative hypotheses, then investigation takes Loeb's concerns seriously, even if that seriousness isn't publicized. November 27th through January 27th is active observation phase. 2 months of continuous monitoring. Spectroscopy measuring composition continuously. Photometry tracking brightness variations. Astrometry measuring position with precision sufficient to detect tiny trajectory deviations. Radio surveys checking for emissions. Polarimetry analyzing dust structure. Every available technique applied systematically. And key questions driving observation are specific and testable. Did 3i Atlas survive perihelion intact? Some comets fragment during close solar approach. Tidal forces, thermal stress, structural weaknesses all contribute to breakup. If 3i Atlas fragments, natural origin probability increases dramatically. Technology might be robust, but comet fragmentation is routine. If it survives intact despite thermal stress and tidal forces, that's data point favoring structural integrity beyond typical comets. Did outgassing behavior change post-perihelion? Natural comets show predictable patterns. Activity increases approaching Sun, peaks near perihelion, decreases departing. Symmetrical roughly. If 3i Atlas shows asymmetric activity, if post-perihelion behavior doesn't mirror pre-perihelion, that's anomaly worth investigating. If it shows unexpected activity changes correlated with planetary proximity, that's stronger anomaly. If it shows activity patterns that don't correlate with solar distance at all, that's potential technological signature. Did trajectory deviate from gravitational predictions? This is critical measurement. If trajectory follows pure gravitational plus standard outgassing models exactly, natural origin is confirmed. If trajectory shows deviations requiring alternative explanations, technological hypothesis remains viable. and deviation detection requires precision astrometry over extended period. Single measurement isn't sufficient. Need dozens of measurements over weeks to characterize orbit accurately, compare to predictions, quantify deviations. Are there electromagnetic emissions? Radio surveys during observation window check for signals. Natural comets don't emit radio, not at detectable levels, not with structured patterns. If 3i Atlas broadcasts anything, if there's any emission beyond thermal noise, that's extraordinary evidence demanding extraordinary scrutiny. Even brief burst would be transformative. Even ambiguous signal would warrant further investigation. Silence is expected. Anything else is revolutionary. December 19th, closest Earth approach at 1.8 astronomical units, is psychological milestone as much as observational one. Maximum proximity. Optimal viewing geometry for amateur observers. Brightness peak. If there's communication attempt, if there's deliberate signal, this is when it would occur. Close enough for efficient transmission, far enough for safety. Perfect timing for revealing presence if presence is meant to be revealed. And if nothing special happens, if December 19th passes like any other observation day, that's data point 2. Suggests if 3i Atlas is technology, it's not designed for obvious contact. Suggests subtlety is intentional. Suggests we're not meant to know conclusively. Late January observation window closes. 3i Atlas fades below detection threshold. Brightness drops. Signal to noise becomes prohibitive. Even JWST can't track indefinitely. At some point, object becomes effectively invisible, too dim and distant for meaningful observation. That's hard deadline. After that, data collection ends. Analysis phase begins. No more new observations, only interpretation of existing data remains. And that permanent closure, that irreversibility, that's what creates urgency. If we miss something during observation window, if critical measurement isn't taken, if important signal occurs during coverage gap, we lose it forever. 3i Atlas doesn't return. It's not periodic comet we'll see again next century. It's interstellar visitor on hyperbolic trajectory. One pass through solar system, one chance to gather data, one opportunity to answer questions. Hesitation costs everything. So what are we actually watching for beyond technical measurements? We're watching for correlations, for patterns, for structure in data that suggests purpose rather than randomness. Natural objects show statistical noise, technology shows signal, and distinguishing signal from noise requires comprehensive data, extended observation, rigorous analysis. That's what next 2 months provide. That's what Observation Campaign enables. That's what makes this investigation potentially conclusive rather than permanently ambiguous like Oumuamua. If correlations appear, if multiple independent anomalies correlate with each other or with external variables, technological probability increases. If brightness variations correlate with Earth-facing orientation that suggests deliberate display, if trajectory deviations correlate with planetary proximity, that suggests responsive maneuvering. If outgassing patterns correlate with observation intensity, that suggests awareness of being watched. Any correlation is meaningful. Multiple correlations are transformative. If correlations don't appear, if everything is random, if all measurements match natural predictions within uncertainty, technological probability decreases. 40% becomes 20%, 10%, negligible. Natural explanations win. Anomalies get explained as unusual but natural phenomena. Loeb's hypothesis gets filed as interesting but unconfirmed speculation. Science moves on. Either outcome requires honest analysis, requires following data wherever it leads, requires resisting temptation to force conclusions that match pre-existing beliefs, requires intellectual humility about uncertainty, requires transparency about methods and assumptions, requires willingness to be wrong publicly if evidence demands it. That's how science works when it works well. That's what Observation Campaign should embody. But here's the fear, here's what keeps me awake. What if data is ambiguous? What if 60 days pass and we're left with same uncertainty we have now? What if anomalies persist but don't intensify? What if natural explanations remain strained but not impossible? What if technological hypothesis remains viable but not confirmed? Then we learned nothing conclusive. Then 3i Atlas becomes Oumuamua Part 2. Another permanent uncertainty, another endless debate, another missed chance at resolution. And that might be the likely outcome. That might be the realistic expectation. Science rarely provides clean answers to fundamental questions. Ambiguity persists, interpretations diverge, consensus remains elusive. But at least we'll have tried, at least we'll have investigated seriously, at least we'll have followed evidence transparently, and that's valuable even if conclusions disappoint. Because next time, if there is next time, if another interstellar visitor arrives showing similar anomalies, we'll have precedent, we'll have methodology, we'll have framework for investigation, we'll be better prepared, we'll waste less time debating whether investigation is warranted and more time actually investigating. So the next 2 months matter, regardless of outcome. They matter because humanity is practicing how to handle this category of question, how to investigate potential technology without premature alarm, how to coordinate globally, how to analyze transparently, how to communicate uncertainty honestly. Those skills transfer, those capabilities persist, and building them now, while stakes are uncertain, prepares us for future when stakes might be certain. When signal is obvious, when contact is undeniable, when questions aren't philosophical but practical. We're learning now for then. And 3i Atlas is the teacher whether it's technology or comet. Either way, we're becoming civilization capable of finding out. And that transformation might matter more than any specific discovery. Because civilization that can investigate honestly can handle truth whatever truth turns out to be. So here we are at the end of analysis and the beginning of uncertainty. Because honest exploration of 3i Atlas doesn't resolve into clean conclusion. It resolves into probability space where multiple interpretations maintain legitimacy, where evidence permits different frameworks, where smart people examining identical data reach opposite conclusions. And that's uncomfortable. Human psychology craves certainty. We want definitive answers. We want clear categories, natural or artificial, real or false alarm. But universe doesn't always cooperate with our cognitive preferences. Sometimes the honest answer is, we don't know and might never know conclusively, and learning to live with that uncertainty while still investigating productively might be most important skill we develop through this experience. 40% technological probability. That's Avi Loeb's number. That's what he calculated using Loeb scale applied to 8 documented anomalies in 3i Atlas. And over thousands of words we've examined why he calculated that number, what methodology produced it, what evidence supports it, what criticism challenges it, what it would mean practically if he's right, what alternative explanations exist if he's wrong. Now the question becomes not whether 40% is correct number, but whether that number, whatever the actual probability is, demands different response than we're currently providing. Science operates by minimizing false positives. Better to miss genuine signals than accept false alarms. That methodology has track record of success because throughout history, natural explanations eventually proved correct for phenomena initially seeming impossible. Pulsars aren't alien beacons, they're neutron stars with extreme magnetic fields. Fast radio bursts aren't communications, they're magnetar emissions during stellar quakes. Tabby's star isn't Dyson's sphere, it's dust clouds from disintegrated comet. Pattern is clear, nature is weird, technology is rare. Betting on natural explanations wins historically, but track record isn't guarantee. Past success doesn't eliminate possibility that eventually, someday, somewhere, we'll encounter signal that genuinely is technology. And when that happens, when genuine signal arrives, what distinguishes it from false alarms we've correctly dismissed? Only evidence, only observation, only analysis. And if our methodology defaults to dismissing technological hypothesis reflexively, if cultural momentum makes investigating seriously career-threatening, if institutional incentives punish scientists who consider alternatives transparently, then we guarantee missing genuine signal whenever it appears because our system is optimized to reject it. That's the metacognitive trap. We've built scientific culture that excels at avoiding false positives but struggles with false negatives. We're excellent at not claiming aliens when natural explanation exists. We're terrible at recognizing aliens if natural explanation is merely improbable rather than impossible. And that asymmetry is fine if technology is so rare we'll never encounter it. But if technology appears occasionally, if interstellar probes or derelict equipment or communication infrastructure passes through solar systems sometimes, then our methodology guarantees we'll dismiss it. We'll find natural explanations that work technically. We'll publish papers explaining anomalies. We'll congratulate ourselves on scientific rigor. And we'll never realize we missed signal because we designed systems specifically to avoid seeing it. 40% means we're in that danger zone, means dismissing technological hypothesis prematurely carries risk comparable to accepting it prematurely, means we need investigation that takes both natural and technological possibilities seriously, tests both rigorously, follows evidence transparently. And I'm not convinced that's happening. I'm not convinced observation campaign is structured to actually test technological hypothesis, rather than just gather data that will eventually be explained naturally through increasingly complex models. Because here's what testing technological hypothesis seriously requires: clear falsification criteria, explicit predictions that distinguish technology from nature, measurements targeted at those predictions, protocols that treat technological signatures as real possibilities worth looking for rather than last resort explanations when everything else fails, and transparency about what would constitute evidence sufficient to shift probability significantly upward. Are those elements present in current observation campaign? Maybe. Workshop established methodologies, protocol standardized measurements, data collection is comprehensive, but is analysis framework genuinely open to technological hypothesis? Or is framework structured to find natural explanations and consider technology only if natural explanations definitively fail? That difference matters enormously. First approach treats hypotheses symmetrically. Second approach loads dice toward natural explanations. And loading dice might be appropriate if prior probability of technology is effectively zero. If we have strong theoretical reasons to believe we're alone in galaxy, if Drake equation suggests intelligent civilizations are vanishingly rare, if Fermi paradox convinces us that silence is evidence of absence, then starting with strong presumption of natural explanations is justified. But if we're uncertain about those priors, if we admit we don't know whether technology is common or rare in galaxy, then loading dice becomes prejudice rather than proper statistical practice. This is where honest disagreement lives. Skeptics believe priors strongly favour natural explanations. Loeb believes priors are more uncertain, that we lack data to confidently assert technology is rare. Both positions are defensible given current knowledge. Neither is obviously correct, and that fundamental uncertainty about priors propagates through every analysis, making conclusions dependent on assumptions as much as evidence. So living with 40% means accepting that probability reflects not just data, but assumptions. Means recognizing that different reasonable assumptions generate different reasonable conclusions. Means understanding that resolution won't come from more sophisticated argument, but from more comprehensive data. Means building tolerance for ambiguity while maintaining commitment to investigation. And personally, existentially, culturally, what does 40% do to us? What does it mean to live in a moment where technological probability attached to real observable object reaches level that demands attention? For some people, it's validating. Confirms suspicion that universe contains intelligence beyond Earth. Provides hope that we're not alone, that cosmic loneliness isn't human fate. For others, it's threatening. Challenges anthropocentric worldview. Raises uncomfortable questions about human significance. Creates anxiety about what contact might mean for civilization that's barely managing its own technology. Both responses are human, both are valid, and managing both while investigating honestly is challenge space agencies face in communicating about 3i Atlas. Say too little, accusation of cover-up. Say too much, accusation of fear-mongering. Maintain measured scientific tone, accusation of dismissing legitimate possibilities. Acknowledge uncertainty explicitly, accusation of not knowing what you should know. It's impossible communication environment. No statement satisfies everyone. No position is safe from criticism, which is why I appreciate what Loeb is doing even if I'm uncertain whether he's right. He's forcing conversation, he's making implicit assumptions explicit, he's demanding that field develops frameworks for handling this category of question rather than avoiding it. And even if 3i Atlas proves natural, even if 40% drops to zero after comprehensive analysis, framework persists. Loeb's scale exists now. Future interstellar visitors will be evaluated using similar criteria. Methodology improves. Investigation becomes systematic rather than reactive. That's progress regardless of 3i Atlas outcome. Over next 2 months, data will flow. Observation campaign will generate comprehensive measurements. Analysis will produce papers. Conclusions will emerge. And whatever those conclusions are, whatever probability assessment results from complete data, we'll have answered important question about whether humanity in 2025 is capable of investigating potential contact honestly and transparently, whether our culture permits following evidence where it leads, whether institutions can coordinate globally on questions with profound implications, whether scientists can maintain rigor while exploring uncertainty, whether media can communicate nuance without sensationalizing, whether public can engage with ambiguity without demanding premature certainty. Those are tests of civilizational maturity as much as tests of three-eye atlas origin, and in some ways those tests matter more than specific discovery. Because civilization that passes those tests can handle contact if contact occurs. Civilization that fails them isn't ready regardless of what universe presents. So maybe three-eye atlas is evaluation. Maybe we're being tested not by aliens but by reality itself. Maybe the question isn't, what is this object, but what are we capable of understanding? And that's test we can pass or fail, independent of whether object is comet or probe. I want us to pass. I want investigation that's honest and thorough and transparent. I want analysis that considers alternatives rigorously without prejudice. I want conclusions that follow data even if data leads somewhere uncomfortable. I want scientific community that can handle uncertainty without retreating into defensive certainty. I want space agencies that can coordinate globally without national ego interfering. I want media that can communicate probability without sensationalizing or dismissing. I want public that can engage with ambiguity without panic or mockery. That's civilization ready for whatever comes next. So as three-eye atlas fades, as observation window closes, as analysis phase begins, remember that we're watching ourselves as much as we're watching object. We're learning what we're capable of. We're testing our institutions and culture and intellectual frameworks against question that matters potentially more than any other. And results of that test, whatever they are, will shape how we approach future encounters, future anomalies, future moments when data permits technological interpretation. Because this won't be last time. Telescope surveys are improving. Detection rates are increasing. More interstellar visitors will be found. And if pattern continues, if anomalies persist across multiple objects, cumulative case for technology strengthens dramatically. But we need practice. We need experience. We need to fail and learn and improve. Three-eye atlas is practice. Next object is test. Object after that is when we'll actually know what we're doing. And by then, maybe 40% won't feel shocking. Maybe it'll feel like reasonable probability that demands investigation without controversy. Maybe we'll have built culture and frameworks and methodologies that handle this gracefully. Maybe we'll be ready. Or maybe I'm wrong about everything. Maybe three-eye atlas is exactly what skeptics say it is. Natural comet with unusual but explainable composition from formation conditions we haven't modelled correctly. Maybe 40% is confirmation bias dressed in mathematical clothing. Maybe Loeb is overreaching, and this entire analysis is elaborate rationalization for seeing patterns in noise. Maybe next 2 months of data will prove natural explanations correct, and technological hypothesis will collapse under weight of evidence. And if that happens, if I'm wrong, I'll acknowledge it honestly because being wrong is how we learn, and learning matters more than ego. But until data resolves uncertainty, until observation campaign concludes, and analysis firms up probability one direction or other, 40% stands as challenge and invitation. Challenge to investigate honestly. Invitation to consider possibilities we're uncomfortable considering. And whichever way evidence ultimately points, the fact that we're asking these questions publicly, calculating these probabilities explicitly, investigating these anomalies seriously, that represents progress. That represents humanity growing into a role of civilization that might encounter other civilizations. That represents us becoming species capable of handling truth, whatever truth is. And that's worth pursuing regardless of what three-eye atlas turns out to be. This isn't just about one object. This is about who we're becoming. This is about capabilities we're developing. This is about civilization maturing into cosmos-aware entity that doesn't hide from possibility of contact, but investigates it systematically. We're living through that transition right now. Three-eye atlas is catalyst. The real transformation is us. And I want to see where we go from here. I want to watch us learn. I want us to succeed. So subscribe if you're still with me. Because this story continues. Data will emerge over next weeks. Probabilities will shift. Conclusions will form, and I'll be here analysing every development, explaining every implication, exploring every question as honestly as I can. Drop comment with your probability. What do you think? 40% too high? Too low? What would change your mind? Join this community of people willing to sit with uncertainty and investigate anyway. Because that's how we get answers. That's how we make progress. That's how we become civilization worth finding if anyone's looking. Thanks for thinking alongside me. Let's see what happens next together.